So we continue today with separation of variables. Remember, to remind you, last time we started in the last video separation of variables. Remember the main idea was to assume that the function has this multiplicative form, then to differentiate this form and to substitute it into the equation, then to obtain certain ordinary differential equations from that equation, then to solve these ordinary differential equations, and once you solve them you find the two functions f and g, you multiply them as in the screen, and that's it. Last time we started this method, we solved this easy example, and we promised to continue with a more elaborated example, that's the wave equation. So today we start the wave equation. When we talk about the wave equation, it's very important to understand the physical meaning behind the wave equation. So in talking about the wave equation, the first thing, we have the modeling part. We have the equation itself, and we have the solution. So these are like three important pillars to the wave equation. So when we talk about the wave equation, remember when we started this chapter, the partial differential equations, we talked about the modeling idea. Remember, modeling means converting a word problem to a math problem. So you have a real life problem that you can describe in words by a paragraph, for example. Then instead of writing many sentences to describe a problem, you convert it into an equation. One equation, two equations, 10 equations. This transformation is called modeling. Now in this course, unfortunately, we will not do the modeling for the wave equation, but you can refer to the textbook. It's the first page, or let's say the first 2 pages of this section, the wave equation. You can read it. If you have some basics from physics, you will understand the modeling part. What we will be doing in this video is we will see the equation, the meaning of the equation, and then we will solve it using the separation of variables method. So in this video, we will be interested in these 2 pillars of the wave equation. So first of all, what is the wave equation? What is the wave equation? So the equation, second partial derivative with respect to t equals a certain constant, second partial derivative with respect to x, and c is positive. Not the equation itself, but this equation together with what we called the boundary conditions. So you have certain boundary conditions, and we will put some effort to understand the meaning of these boundary conditions. U of 0t equals U of LT equals 0 when t is bigger than or equal to 0. U of x 0 equals little f of x. U sub t of x 0 equals gx when x is between 0 and L. So these together, so if you look at the equation, and not only the equation, you look at the equation together with these conditions, all of them as one unit. So I'm dealing with these as one unit. All of them will be called the wave equation. So this is the wave equation. Now, how do we solve this equation? This will be done using the separation of variables. But before solving, as we mentioned earlier, let's see what do we mean. So what is the meaning? What is the meaning of the wave equation? This is the first part that we need to understand. Again, before this, I encourage you, if you have some background in physics, to review how to find this equation. Okay, so I will discuss now the meaning of the equation, but how was this equation found? Try to review it from the textbook, Kreisig book. Okay, so the idea the idea. We have a vibrating string. We have a vibrating string. And remember, when we talk about a string, what kind of string do we have? What kind of string do we have? We have a string that's homogeneous. When we talk about homogeneous strings, we mean a string whose mass on every unit of length is the same. So you're talking about a homogeneous string. This string is elastic. It has a coefficient of elasticity. This is related to the C. The C here is related to the elasticity of the string. We're not going in this direction, but we have a vibrating string. This string has length L. This string is placed on the x-axis, and because its length is L, it is placed from 0 to L. So if you imagine the xy plane, so where is my string? You have a string of length L. It is fixed on the bound, so this is 0. This is the length L. For example, the length was 5, the length was 10, and so on. Now, you have a string. For example, let's say this was the initial position, for example. This was the initial position, okay? And then you give this string a certain force that causes some motion. So imagine this string, just imagine it. This string will keep moving because you know Newton's law of motion says a moving particle keeps moving, right? If you don't, for example, give it another force, if there is no friction, so it will keep moving to infinity. So imagine we have this string put in an ideal case. You don't have any friction, any other force that affect this string. So again, you have this red part. Let's say this is the initial position of the string. You give it a force. You just like slap it. Then it will start vibrating. Now, when it vibrates, the y-axis, I will use the y-axis to describe u, the x-axis to describe x. So what is x? So x is the position on the string. So for example, if you say x is 1, that means you have the string after one unit of length on the string. Okay. What is t? T is the time. T is the time. And what is u? What is u? It is the position of the string after t units of time. So what is the idea? The idea is you have this vibrating string, and I'm sure we all agree it will keep vibrating. Let's say this is like another moment, and this is like another moment, and so on. So just imagine this. You have infinitely many moments according to time, and this string is vibrating all the time. So just imagine you have like a screenshot. So when the time is 1, you have a screenshot for the string. It will give you a certain function, like the green function, for example. After 2 units of time, you have a screenshot for this vibrating string. It will give you another function, and so on. So at each certain time, there is a screenshot of this string. Now, this string is always fixed here. So on the ends, it doesn't move on the ends. So it is like it is nailed here and here. Okay. So at each time t, at a certain moment, you take a screenshot. For example, this is what you get. So this means this is the u, this is the x. This is what we mean by u of x and t. So when t is fixed, you just have one variable, that's x. You draw this function. It's just a function. It is just a function. Imagine a function like x squared. Imagine a function like sine x, and so on. Okay, so this is the meaning of ux and t. Okay, so u of x and t, this is the position of the string after t units of time. What do we mean? Let's forget this for now. Okay, what do we mean by u of 0t, this one, equals u of lt equals 0? This is exactly what's meant by saying the string is nailed at the ends. So you nail it here, it's not moving. So what is the position at those two endpoints? It's always 0, regardless of time, at any moment, at any time. The endpoints do not move, so they are always at 0. This is exactly the meaning of this condition, these two conditions, okay? Then u of x 0 equals f of x, u sub t x 0 equals g of x. What does it mean? So again, u0t equals ult equals 0 for all t bigger than 0. This means that the string is nailed at the endpoints. Okay, we agreed on this. What do we mean by u of x 0 equals f of x? When we say u of x 0 equals f of x, this 0, this represents the time. So it's like saying the time is 0. But remember, when you study any physical phenomena, if t is 0, that means the initial, right? For example, the initial velocity, the initial position, the initial what? Because you're dealing with u, and u describes the position of the string. So basically, u of x 0 equals f of x. This represents the initial position of the string. When we say initial position, it doesn't mean the time is 0, because what is the meaning of time 0? The time equals 0, it means the moment you started your study. For example, I have a vibrating string, for example, since the last year, okay? Just imagine, because we're saying this string keeps vibrating just infinitely, okay? It doesn't stop vibrating. So imagine you have a vibrating string, and you're not caring about this string, but at a certain moment now, at this moment here, you said, okay, I want to study this string. So at this moment, you looked at the string, and at this moment, you found the string. For example, when you took a picture for this string at this certain moment, you found it like this. Then you say, okay, I am interested in this shape, in this string at this moment. This will be exactly your function. So this is a function, right? This is a graph of a certain function, and this will be the initial position. So when we say initial, again, when we say initial, it means the moment you started your study. It doesn't mean time 0, literally, because what is the meaning of the time being 0? Okay, so again, you started your study. Now you take a screenshot for that string. Now this function here, whatever you get, this is the function that's described by the equation u of x 0 equals f of x. Then you have the other condition. So this is the initial position. You have the other condition, u sub t of x 0 equals g of x. So in this condition, you are differentiating with respect to t at time equals 0. But remember, when you differentiate with respect to t, so you are differentiating with respect to t, this means the velocity, right? All the time, if you have a motion and you differentiate with respect to the time, that gives you the velocity. So this tells you, and the time equals 0. So basically, this tells you about the initial velocity of the string. So what is the meaning of g of x again? G of x, it means this. This string is vibrating. So at each x, the string is vibrating. For example, let's make another drawing. So this is 0, this is L. These are the x values, right? So at each x, if you look at this x, the string is vibrating. Vibrating means it's changing with time. For example, when the time is 0, it was here, for example. When the time is 1 is here, when the time, and so on. Anything that changes, it has a velocity. So the velocity at this x, it has a certain value. Then you have this x, and the string is vibrating. So the initial velocity at that x has a certain value. The initial velocity at this x has a certain value. So imagine you have an initial velocity at each single x on the string. So after all, if you look at the string, let's say this is the string, okay? At each x, there is a velocity. Now, this velocity is given by g of x, okay? So the velocity at time equals 0 is given by g of x. This is the meaning of g of x. So for example, if g of x was x squared, for example, we're saying, if g of x was x squared, that means the initial velocity when x is 1 is x squared, that's 1 squared, that's 1. When x is 2, that's 4. So the initial velocity is 4. So if you go at position 2 on the string, the initial velocity, the velocity at the moment that you started your study is 4. This is exactly the meaning of the function g of x. So in summary, what do we have? So in summary, we have this wave equation. Now, how did this equation result? It is from the modeling part. Okay, remember from the beginning we said there is the modeling part that we did not do. But if we do the modeling for this vibrating string, we will find this equation. Now, what is the meaning of the given conditions? We explained them. So this means the string is nailed at the end points. These are the first two conditions. The other two conditions are giving you the initial position and the initial velocity of the string. Now, what is it that we want? So what do we want? We want to find the position of the string at any time t, given what? Given four things. What are these four things? Given that u0t equals ult equals 0 for all t, given that u of x0 equals f of x and u sub t x0 equals g of x. So we are given only, okay, this is very important to understand. You are only given that the string is nailed at the endpoints. You are only given that you are given the initial position and the initial velocity. From these four things, only from these four things, you need to determine the position of the string at any time t. So if I give you the position at the first moment, the initial position, then you're asked to find the position after 10 units of time, 100 units of time, and so on. Now, how are we going to do this? We're going to do this by solving the partial differential equation. So we will solve this differential equation, and once we solve it, it gives us a function in terms of time, and then at any time you plug that value for time, you get your position. So let's see. So now after understanding, I hope after understanding the equation, let's see how to solve the equation. So solving the wave equation. Before we start solving, let's look at the condition u of 0t equals 0 for all t. So at any time, at any moment, the string is nailed at the endpoints. This is the first endpoint at 0, and the other condition u of lt equals 0. Let's look at this first condition. Okay. Now we want to solve by separation of variables. What do you mean by separation of variables? We mean to assume that the solution has this form, right? F of x, g of t. So we assume that the solution has the form f of x, g of t. This is the main idea of separation of variables. But if you assume your solution to have this form, then what is the meaning of u0t? That means f of 0, right, because x is 0, g of t equals 0, and this is true for all t bigger than 0. So regardless of the value of t, this will be 0. But this is a product of two functions, right, of two values. So this implies either f of 0 equals 0 or g of t equals 0, right? But g of t equals 0, that has to be for all t bigger than 0. And we need to distinguish between f of 0 equals 0 and g of t equals 0 for all t. What is the difference? For example, if you take the function f of x equals x squared, when x is 0, what is f of 0? It is 0, right? When you take the function, for example, g of t equals t squared, when t is 0, you get 0. But is it true that g of t equals 0 for all t? Is it true that you substitute any t and you get 0? It's not true. So when we say g of t equals 0 for all t, that means the function is 0. If you substitute any t, it gives you exactly 0. So why are we giving so much effort to this? Because if g of t is equal to 0 all the time, then what is u of xt? Remember, u of xt is f of x times g of t. But if g of t was always 0, then regardless of f, this product will be 0, right? So you're saying that u of xt equals 0. So you're saying that the position of the string is always at 0. What does it mean? It means that you are studying a string, you are studying a vibrating, remember, a vibrating string whose position is always like this. So basically there is no vibration, right? There is no vibration. So in fact, this case, the g of t equals 0, for us this case is rejected. There is no way g of t is equal to 0 for all t. So the condition that u of 0t equals 0 implies either f of 0 equals 0 or g of t equals 0 for all t. G of t equals 0 for all t, this is rejected. It cannot be true because then there is no motion, there is no vibrating string. So from the condition u of 0t equals 0, we will conclude that f of 0 equals 0, and similarly, the condition u of lt equals 0 implies what? It implies that f of l equals 0. So basically we have two conditions before we start our solution. We have two conditions on f. These are like boundary conditions for f. Remember, what is f? F is one of those two functions which make our solution. Our solution is a product of f of x and g of t. Okay, so this is before solving. We wanted this remark. It is very important, you will see. So now we start the solution. So again, to solve the wave equation, we start by separation of variables, and this is what it means. Now, what is the wave equation? The wave equation is the second derivative with respect to t is equal to a certain constant, c squared. This constant, it could be any number, just imagine it, 1, 9, anything that's positive, times the second derivative with respect to x. So basically you're differentiating u twice with respect to t, but if you differentiate it twice with respect to t, that means you're keeping f as a constant, and you're differentiating g twice with respect to t. Then if you differentiate it twice with respect to x, you're differentiating the f, and you're keeping the g as a constant. So if you substitute these derivatives into the equation, the u sub tt is f g double prime, the u sub xx is f double prime g. Remember all the time, when you apply the method of separation of variables, you're converting the partial differential equation into an ordinary differential equation having many functions, like the f and g in our case. Now remember, the main idea now is to separate f and g. So the question now, can you separate in one side f, and the other side g? Yes, we can. For example, here we can say f double prime over f equals g double prime over c squared g, right? And why is this so important? Because at this point you say, okay, this side is completely in terms of t, and this side is completely in terms of x, and we agreed that for this to be true, and this is the main idea of separation of variables, for one side in terms of t to be equal to another side in terms of x all the time, that means there must be a constant k. So k is just a number, we don't know it yet. There must be a number k where the two sides are equal to that number k. Okay, now why is this important? Because then you can say, okay, g double prime over c squared g equals k, and f double prime over f equals k. Cross multiplication, g double prime minus c squared kg equals 0, and f double prime minus kf equals 0. This is the important part of the separation of variables. Separation of variables, you start with a partial differential equation like this, then you assume your function, your solution having the form f of x g of t, you reach two differential equations. We hope to have two simple differential equations, and I think we all agree these two equations are really simple. So now what we do is we start solving these differential equations. So now we solve fw prime minus kf equals 0, then we solve gw prime minus c squared kg equals 0. But now I'm going to start with fw prime minus kf equals 0, and the reason is what we did before we start solving. Remember, before we started, we had this condition and this condition enough, right? So now I'm going to say, okay, I want to solve this equation, adding to it f of 0 equals f of L equals 0. So basically I'm solving not an ordinary differential equation, I'm solving an initial value problem. I'm having an ordinary differential equation together with two boundary conditions, and that will help me find the constants after finding the solution. So this is why we started by analyzing the conditions to have f of 0 and f of L equals 0. Okay, so now we solve this. fw prime minus kf equals 0. This equation is a second order differential equation with constant coefficients. And I think when we did the ordinary differential equations, the easiest equation was the constant coefficients equation. Why is it the easiest equation? Because then, remember, you assume your solution to have the form e to the lambda x, then you will have this characteristic equation, and you just solve it. So lambda squared equals k. And at this point, just imagine the k. The k is any number. For example, the k was 1, then the lambda would be plus minus 1. If k was 2, 4, then you will have two values for lambda. But remember, in differential equations, it is very important to notice the values of this k. Why? Because, just to remind you, for example, if you're solving the differential equation yw prime minus 4y prime plus 4y equals 0, the characteristic equation would be this. And this will give you lambda minus 2 times lambda minus 2 equals 0. So that means you have the 2 repeated. In this case, you have two solutions. One of them is e to the 2x, but the second solution would be x e to the 2x. While, for example, if you have yw prime minus y equals 0, and the characteristic equation is this, so the lambda square equals 1, so the lambda is a plus minus 1. In this case, you have two different solutions, e to the x, e to the minus x. So it's very important to distinguish between having the same root repeated or different roots, because when you have the same root, then you will need to multiply the first solution with x. This is very important to remember from differential equations. Why are we saying this? Because now you have this quadratic equation, lambda squared equals k. Imagine k was 0, then the only value for lambda is 0. That means you have the 0 repeated, which forces you to multiply with x. But if k was, for example, 4, you will have two different roots, 2 and negative 2. If k was negative, then you will have imaginary numbers, complex numbers. And that means you will need to deal with cosine and sine. So at this point, unfortunately, it is unfortunate, we will have to deal with three cases. The first case, let me start with the easy case, that k equals 0. If k equals 0, then lambda squared equals 0 will have only one solution, but this solution is repeated. So what is the general solution? It's c1 times the first solution is e to the 0x plus c2, the second solution is x e to the 0x. So basically you're dealing with c1 plus c2x. This is your f. Okay? So fine, we found f, and it is very natural to have two constants because we're dealing with a second order differential equation. But we are so lucky to have f of 0 equals 0 and f of L equals 0, right? So f of 0 equals 0, that means you substitute 0, you get c1 equals 0. And f of L equals 0, that means c1 plus c2L equals 0. But if c1 is 0, then you conclude that c2L equals 0. And this is a product. This is a product of c2 and L equals 0. It means one of the two quantities has to be 0. Either c2 is 0 or L is 0. Now, the L being 0, this is, of course, rejected. Why is it rejected? Because L is the length of the string. And if you're studying the vibration of a string of length 0, this doesn't make any sense, right? There is no string of length 0. And if C2 was 0, then if C2 was 0, we already know that C1 is 0, right? So if you go back to this, so C1 is 0 and C2 is 0, that implies that F is 0. But if F is 0, then what's U? U is Fg, and if F is completely 0, then U is 0, and again, this is rejected. Remember, you're studying a vibrating string. If you're saying the U is 0, you're not studying anything. So basically, what we're saying now is that case 1 is completely rejected. Everything that results from the first case is rejected. So you can't have k equals 0. So that means let's go to the second case. What is the second case? Remember, we are classifying our cases according to this equation, lambda squared equals k. If k was 0, everything is rejected. Now we need to talk about what happens if k was positive. If k was positive, you look at the equation lambda squared equals k. For example, lambda squared equals 4. Then lambda is plus minus root k. I think we all agree on this. And in this case, your solution would be a constant times e to the root kx plus c2 e to the negative kx, right? But again, you have two conditions, f of 0 equals 0 and f of l equals 0. If you substitute 0 into this function, you get c1 plus c2 equals 0, which means c2 is negative c1. And if you substitute L, you get C1 e to the root KL plus C2 negative root KL equals 0. If you use C2 and replace it by negative C1, you get C1 e to the root KL minus C1 negative root KL equals 0. If you factorize the C1, you get e to the root KL minus e to the negative root KL equals 0. But at this stage, you have a product that's equal to 0. So again, you will have two cases. It's either C1 is equal to 0 or e to the root KL minus e to the negative root KL equals 0. If C1 was 0, we know that C2 is negative C1, so it's already 0, right? But if C1 and C2 are zeros, then what is F? F is this, right? So if you take this F here and you substitute C1 and C2 to be zeros, then what is F? It is completely 0. But if F is completely 0, then what's U? It is 0, and this case is rejected. So there is no way you have C1 equals 0, because then you will have no vibration. You will not have any vibration. Okay, then maybe e to the root KL minus e to the negative root KL is 0. But this means that e to the root KL equals e to the negative root KL. And if the exponentials are equal, the powers are equal. So root KL is negative root KL. If you move 2, negative root KL is 0. And again, this is a product that's equal to 0. So either k is 0 or L is 0. L is 0. This is rejected because L is the length of the string. And k is 0. This is rejected because we are dealing with the case k bigger than 0. So here, again, everything is rejected. So what does this mean? So we started the second case, that k is positive, and we discovered that everything that results from this case is rejected. So again, my conclusion is like the first case. So case 2 is rejected. So far we have two rejected cases. K cannot be positive, k cannot be 0. So maybe the third case is like our lucky case. So what is the third case? K is negative. K is negative. Remember, our equation was lambda squared equals k. And before we solve, just imagine we reach a rejection again. So imagine in the end, we say this case is rejected. What does it mean? Then this means we can't solve this equation using this method, simply like that. Okay, so maybe there is another method to solve this equation. But we will be lucky to have a solution. You will see. We will accept something from this case. So now if k was negative, imagine k was negative 1. Okay, imagine k was negative 1. So it's lambda squared equals negative 1. In this case, what is the lambda? It's a plus minus what? Plus minus I, right? The I, it comes from the negative. The I, it comes from the negative. So here, lambda square equals k. What is the lambda? It's a plus minus. Let me write the k as negative k. When k is negative, this is our case. When k is negative, this number here is positive, right? Negative k will be positive. So in fact, what happens now is this. This negative here, this gives you the I, and this positive negative k, this gives you the root. So this is what we will have in this case, okay? Okay. So in this case, what is the solution? It will be a constant times the cosine root negative kx plus another constant times sine negative kx. Again, we have two boundary conditions, f of 0 equals 0 and f of L equals 0. F of 0 equals, if you substitute, you get C1 equals 0 right away, right? F of L, what is f of L? It's C1 times cosine, but C1 is 0, so there is no need to write it. So you'll have C2 sine root negative KL equals 0. Now this gives you again two cases. It's either C2 equals 0 and this is rejected. Why is it rejected? Because we have already C1 equal to 0. If C1 and C2 are both zeros, then the function completely is 0, and that's rejected. For the second case, so maybe we will have sine negative KL equals 0. And the question now, what are the angles whose sine is 0? So this angle, negative root KL, it could be 0, it could be negative pi, negative 2 pi, and so on, or maybe pi, 2 pi, and so on. So these are all integer multiples of pi, the 0, the positive, and the negative integer multiples of pi. Now for the 0, this can't be true because the k is negative, with the negative, this is positive, right? And L is the length of the string, so it's positive, so there is no way you multiply them, you get 0. There is no way you multiply them, you get negative. So in this case, we're saying that root negative KL has to be some integer times pi, and what is n? It's 1, 2, 3, and so on. And the nice thing, we're not rejecting this case. This doesn't give me any reason to reject this solution. So from this, we get k. What is k? It's n pi over L squared with negative. So we have infinitely many possible values for k. We have infinitely many values for k. We can call them kn because the value depends on n. So in the end, we found f. What is f? F is C1 cosine, but the C1 is 0. C2, there is no need to say C2, it's just a constant, right? Times sine root negative k. What's root negative k? It's n pi over Lx. And what is the n? It is 1, 2, and so on. And because again these are infinitely many solutions, let's call them Fn with Cn. So at this stage, we have the function f. Let's go back. Why did we find the function f? We found it because in solving the partial differential equation, we reached this line here. We reached two differential equations. One of them was about f, the other was about g. Now we started with the f equation, and again the reason we started with the f equation is that we have these two conditions about f, we don't have them about g. So that's the reason behind starting with the function f. After solving for f, we found the exact value for k. So now when I solve for g, so now we solve gw prime minus c squared kg equals 0. When we solve this equation, we don't go through the cases, k positive, negative, or whatever, because we have already found the k values. These are the k values. They cannot be anything else. They must be this for f to be satisfied, okay? So basically, we're solving gw prime minus c squared, and what's the k? It's negative, so this becomes positive, and pi over L squared g equals 0. But again, this is with constant coefficients. It has a characteristic equation that's lambda squared equals negative n pi c over L squared, and clearly this is negative, so the lambda is plus minus n pi c over li. But this means what is the g? It is a constant. It is a constant times the cosine plus another constant times the sine. And again, these functions depend on the n. The n, remember, the n was from 1 to infinity. These are the integer values. So, in summary, this is gn, that's fn. So basically now we say, okay, so what is the function u? The function u is the function f times the function g. But we have infinitely many choices for f and g. That means you have infinitely many choices for the un. So what is fn? Fn, you just copy that, right? It's cn sine n pi over lx times what is the gn? It's an cosine n pi c over lt plus bn sine n pi c over lt. Again, the n are the integer values. If you take this constant, the cn, if you take it into the bracket, you just multiply cn with an, you recall it as an, cn bn, just call it bn. So basically there is no need to write the cn. So this becomes like this. So in the end, not in the very end, in fact, in the end, we reached this un, and these are not one solutions. These are infinitely many solutions, and each of these solutions, they satisfy what? How did we find these solutions? We started with this equation. We analyzed these conditions. So basically this solution, the un, it satisfies these three stuff. It satisfies the equation, the differential equation. It satisfies these two boundary conditions. But remember, our solution, we wanted to satisfy two other conditions. We wanted to satisfy, if you go back, this thing, the initial position and the initial velocity conditions. So now I want u of x 0. So we want u of x 0 to be equal to f of x. What is f of x? It could be any function. It could be x squared, for example. It could be sine x, cosine x, anything. But if you try to substitute, if you say, okay, this is my solution, and what is u of x 0? So basically, if you substitute 0 into t equals 0 into these functions, what do you get? If you substitute t equals 0, you will get an sine n pi over lx equals f of x. But imagine f of x wasn't a sine function. Imagine it was x minus 1, for example, or x squared minus x, or anything like this. So at this stage, you discover something could be wrong. You're just saying that I found the solution. We have infinitely many of them. Those solutions satisfy the equation together with two conditions, but they're not satisfying the other two conditions. So now we start asking, how can we satisfy the other two conditions? How can we satisfy the other two conditions? The idea, let's go back a little for just a quick revision about ordinary differential equations. Imagine you have yw prime minus y equals 0 together with two conditions, y of 0 equals 1, y of 0 equals 2, y prime at 0 equals 3, for example. You start solving and you find the characteristic equation from which you have lambda equals plus minus 1. And this gives you two solutions, y1 e to the x, y2 e to the negative x. In our case, I want to connect this stuff together, okay? In our case, I have infinitely many solutions. I have these UNs. These are infinitely many solutions. Now, in the case of a second order differential equation, it's a way simpler than that. We just have two solutions. But if you look at the first solution, it doesn't satisfy either conditions, right? So the first solution does not satisfy this and does not satisfy this. The second solution does not satisfy either conditions. So then we're not saying we don't have a solution, right? At this stage, we say, okay, we have a general solution, which is C1 times Y1 plus C2 Y2. And then we find C1 and C2 to satisfy these conditions, right? So in solving differential equations, you have a fundamental set of solutions. Remember, this terminology was mentioned in the ordinary differential course. So you have a basis for the solution. These are the y1, the y2. If you have a third order differential equation, you would have three solutions forming the fundamental set of solutions, and so on. But then to satisfy a given in a 2 or 3 or whatever, a set of initial conditions, to satisfy these conditions, you must form the general solution. What is the general solution? It is C1y1 plus C2y2. If you have a third order, if you have a fourth order, and so on, right? Now, in our case, we're not able to fulfill certain conditions, right? We're not able to satisfy u of x0 equals f of x. So the idea is you're having infinitely many solutions. Okay, then we form kind of the general solution. What is it? It is the sum of all these solutions multiplied with constants. So you take the first solution multiplied with a constant, the second solution with a constant. But because you're having infinitely many solutions, we're adding the sum notation. So this is like C1u1 plus C2u2 up to infinity. This is the sum notation. And again, this Cn, it will be absorbed by the bracket. You just insert it to the brackets. And what you get is the sum from 1 to infinity. And you just write the UNs. These are the sine times this. So this is what we expect. This is what we expect to be our solution. But still, we have not satisfied the conditions. So now we need u of x0. We need it to be f of x. And remember, the x values are between 0 and L. Now, what is the meaning of ux0? That means you go back to u, this boxed formula, and you replace t by 0. But if you replace t by 0, you get the sum from 1 to infinity sine and pi over Lx times an. This is equal to f of x, right? This is exactly what you get when you substitute t equals 0. Now, when you look at this formula here, this last line, this side here, I'm sure it reminds me of the Fourier series of an odd function, right? Because the sine is an odd function, and the Fourier series is completely composed of sines. We're not seeing any sines, so the function is odd. And this an, if you agree, this plays the role of bn in the Fourier series. Remember, when you have an odd function, this is how the Fourier series looks like, right? This is how it looks like. So this bn is like the an there. Now, what was the formula for the an? The bn, I mean, which is the bn now, the an, sorry. So the formula was 1 over L, integral from negative L to L, the function times sine and pi over Lx dx. But my function f of x is not given on the interval negative LL, because we agreed from the beginning, this function is given over the string, and the string is placed over the interval 0L. But because we're saying that f is odd, and the sine is odd, the product of two odd functions is even, and the integral of an even function from negative L to L is just double from 0 to L. So basically, this is exactly the formula for an. So what we found now is this is the u, and inside the u there is an an. What is the an formula? This is it. We found it. Now what remains is to find. So now we need to find the bn. And how are we going to find the bn? From the last condition, which we haven't used yet, which is u sub t x0 equals gx, right? Now, what is the meaning of u sub t x0? You go back to u, this is your u, you differentiate it with respect to t. Now, when you differentiate with respect to t, we have the sum. This is the sum. The sign will not change, right? The sign will not change, okay. But you need to differentiate the other bracket with respect to t. When you differentiate this bracket, this bigger bracket, when you differentiate it with respect to t, the cosine gives you a negative sign, right? After substituting 0, because you want that when t is 0, it gives you 0. So basically this term vanishes, it doesn't give you anything. But the other term, this term, when you differentiate it, this term, when you differentiate the sign, it gives you cosine, and when you substitute into the cosine, it's not 0, it's 1. So basically that term gives you Bn cosine the angle. When you substitute 0, you get 1 times the derivative of the angle, which is n pi c over L, right? This is exactly what you get, and all of this has to be equal to g of x. So now, again, when you look at this, this is exactly the Fourier series of a certain function. And this is exactly because this is the coefficient of sine. This is now the Bn. But what is the Bn formula? What is the Bn formula? So Bn times n pi c over L. This is the Bn. What is the formula? It's 1 over L, integral from negative L to L, g of x sine n pi over Lx dx. But again, because the g is composed of sines, it is an odd function. So this integrand here is an even function, and the integral of an even function is double from 0 to L. So basically, what is the Bn? It is 2 over n pi c integral from 0 to L g of x sine n pi over Lx dx. This is the Bn. I think at this point we need the summary of the solution. So basically the solution of the wave equation, and remember the wave equation is one unit. It's an equation together with four conditions, four boundary conditions. So the solution of this is u equals the sum. So I'm just copying this u. It is sine n pi over Lx times an cosine n pi c over Lt plus Bn sine n pi c over Lt, and the n is from 1 to infinity, where what is the an? The an formula is there. It's 2 over L integral from 0 to L, the given function f of x times the sine. And what is the Bn? The Bn is what we just found, 2 over n pi c integral from 0 to L g of x sine n pi over Lx dx. So this is exactly the solution of the wave equation. Now, what does it mean, and what is f, what is g? These are given. So just imagine you have a given f of x, like for example x squared minus 1 or x squared minus x or so, or whatever, and the same for gx. You just find these integrals and you plug them back into the equation, and that's it. This is your u. This is exactly your u. For example, let's write the solution of the above wave equation f. So imagine I'm giving you c is 1. I'm telling you that, okay? I'm telling that c is 1. I'm telling you that L is pi, so the length of the string is pi. This is given. You are given the initial position to be, for example, x squared minus pi x, and you are given the initial velocity to be 0. So imagine you are given this, and all the time you will be given, in practical problems, you will have the initial position, you will have the initial velocity, you will have the string length, and you will have the c, because again the c comes out of the elasticity coefficient, which is known for any particular string. Okay, so if you have these parameters, how do you find the solution? This is the solution, this is the u, okay? But all you need to find before writing the u is the an and the bn. And now the nice thing is that bn is 0, because the g is, this is the bn formula, and because the g is given to be 0, that means the initial velocity is 0. So right away the bn is 0. So basically you need to find the an. What's the an? It's 2 over L. L is given to be pi. Integral from 0 to L, that's from 0 to pi. The function is x squared minus pi x times sine n pi over L, that's basically an x dx. So now we need to find this integral. We find it, that's fine, right? So this is u, this is dv, the u is x squared minus pi x, this is sine and x, you differentiate twice, 3 times in fact, you integrate, then this, plus minus integral. Now the last term will be 0 because you are multiplying with 0. This term will be 0. So basically what we have is only the first multiplication, which is x squared minus pi x, this term, times the negative cosine. So basically it becomes pi x minus x squared times the cosine over n. Then as we agreed, the second term with the sine, it vanishes, it is 0, because when you substitute the limits it gives you 0. And then we have plus 2 cosine nx over n cubed. And the limits are from 0 to pi. So this is our integral, and I will need to erase this, okay? I will need to erase this. Okay. So now you substitute the limits. When you substitute pi, you get 0. When you substitute 0, you get 0 in the first term. So basically the first term vanishes. So what's left in fact is 2 over pi and only 2 over n cubed. You substitute cosine and pi minus cosine 0, that's 1. So this is 4 over pi n cubed times negative 1 to the n minus 1. Which is, we know it, right? This is 4 over pi n cubed. So this is negative 2 when n is odd. And this is 0 when n is even. So in fact, the summary is negative 8 over pi n cubed when n is odd. It is 0 when n is even. Now once you reach this, we are done. So basically now we go back to the solution. So what is the solution? Remember, the solution is the sum, and from 1 to infinity, you have sine n pi over lx. I'm copying this solution here, okay? We agreed that the bn is 0, so you will just have the an times cosine n pi c over lt, and we have the an, right? You have the an. So this is the sum from 1 to infinity. What is the an? It's negative 8 over pi n cubed only when n is odd, because when n is even, everything is 0. Sine n pi over lx, cosine n pi, and what is the c? Sorry, I missed this. The c is 1, the l is pi, so there is no need to write them. So in this line, n pi over l, that's just an x, and the cosine and t, because the c is 1, the l is pi. And instead of writing it this way, we saw these ideas from the previous chapter. This is negative 8 sine 2n minus 1 x cosine 2n minus 1 t, all divided by pi 2n minus 1 cubed. This is because n is odd, so we replace every n by 2n minus 1. So in fact, this is our solution. Now, what does it mean to say this is our solution? Because this solution doesn't look so easy. And how do we relate it with the string? The idea now, so this is the summary, this is the position of the string at any time t. So the idea now, for example, are you interested in the position of the string when the time is, for example, 1, for example? Okay, then what is the u? How does the string look like after 1 unit of time? It's very easy. You say, okay, from 1 to infinity, you replace t with 1. You replace t with 1. When you replace it with 1, what do you get? You get negative 8 sine 2n minus 1x cosine 2n minus 1, because the t is 1, over pi 2n minus 1 cubed. Now, if you look at this summation, this has only one variable, that's the x, right? So you start substituting. For example, you take n is 1, you get something in terms of x. N is 2, n is 3, and so on. So in the end, this is just a function. This is a function in terms of x. If we are able to draw it, just imagine, we're saying just imagine, when you draw this function, just imagine you get something like this. Then this is the string. This is the string after 1 unit of time. So if you observe this string while it's moving and you take a screenshot of it after 1 unit of time, this is how it looks like, okay? Now, if you want to understand it more, for example, just take a partial sum. For example, if you replace the infinity by 10, just, you have computers these days, you have MATLAB. So I take this sum, substitute, for example, the sum from 1 to 100, for example, and you plot it. When you plot it, whatever you get, this is the string after 1 unit of time. You're interested in this string after 2 units of time, then you go back to the u and you replace t by 2. You're interested in this string after any unit of time, you replace that t by that value, and you will get the position of the string after that unit of time. So this is the meaning of the wave equation. This is how we solve it, and after solving it, what is the meaning of the solution? I hope this is clear for the wave equation, and that's it for the wave equation. If we have time, we will have one video about D'Alembert solution for the wave equation. So after solving, and if you agree, this is a very long solution for the wave equation, and please, it's very important to notice, it's not about the wave equation. It is about the ideas. So in solving the wave equation, we crossed many ideas on the way, right? So let's go back. So the idea is to understand the solution by separation of variables. So we started with the wave equation. Remember, the first part was understanding the meaning of the wave equation. Let's forget that. Now I want to solve with it using separation of variables. The first thing, we analyzed the given conditions to find boundary conditions about the f. Then we started the separation of variables. We encountered many cases. This is what we need to understand from the solution. So forget wave equation or heat equation or whatever. We're not asked to memorize these forms of solutions, but we need to understand what's going on, and we need to understand when to decide to go with cases. Why did we classify our solution to different cases? Why did we have to talk about 3 cases? Why did we reject? Why did we accept? This is what we need to understand from this long solution. And next time, if we have time, we will do a D'Alembert solution. If not, we will go directly to the heat equation and to solve it again using separation of variables. I hope this is clear.